Welcome to our third equilibrium video tutorial. Today I'm going to show you how we can calculate the equilibrium constant. We'll calculate a numerical value for it. In the first lesson we learned how to write the equilibrium constant expression, and today we'll learn how we can start using it. We can calculate a value for KEQ if we know the concentration of the reactants and products of a system at equilibrium. So let's look at a sample problem here. So we've got, just give myself a little more space. Here we have an equilibrium expression, a balanced equation, carbon monoxide and hydrogen combining to form methanol. And this question is asking us, what is the value of the equilibrium constant? So that's KEQ. So that's what they want to know. The temperature is 330 degrees Celsius, which I mentioned in an earlier lesson isn't important for solving the problem, except that KEQ will be different at different temperatures. So if this was done at a different temperature, we would probably get a different answer for KEQ because these values would be different, but we don't use that in our calculations. We're going to calculate that constant at this temperature if the following concentrations were measured for carbon monoxide, hydrogen, and methanol. So we start by writing an equilibrium constant expression. So just a little review. In the numerator we've got the concentration of the products, and in the denominator the concentration of the reactants. And then we want to remember that if we have any coefficients in the balanced equation, that we raise those concentrations to an exponent that comes from that coefficient. If we want to calculate a value for KEQ now, all we need to do is sub in the values that were given in the question. So in the numerator, the concentration of methanol, 0.055 moles per liter. In the denominator, the concentration of carbon monoxide and the concentration of hydrogen. And it looks something like this, and that will be squared. So then you have to get out your trusty calculator, and let's see what we've got. So I've got 0.055 divided by 0.17 divided by that number, and I come up with a number which is about 399,419. So let's round that to two significant digits. I get 4.0 times 10 to the 5 for my KEQ. So you might be wondering at this point, what happened to the units? We've got units up here, no units in the answer. Well, you may be delighted to discover that KEQ is a unitless number. The reason for this is, if we take a look at what the units work out to be, here moles per liter cancel out. We're left with moles per liter all squared in the denominator. So if we were to work out the units, they would be liters squared per mole squared. These are meaningless physically. This doesn't actually mean anything very exciting. They're just units. And if you think about it, since in different balanced equations, different things will be squared or cubed, and we'll have different numbers of reactants and products, these units are going to be different every single time we calculate them. They're not going to be the same from reaction to reaction. So they don't have any meaning, and so we do not need them. So, unitless number, KEQ, 4.0 times 10 to the 5. This is a very large value for KEQ, and if you remember what we learned about KEQ, that means products are favored. There are more products present in general than reactants at equilibrium. Our next question comes at the problem from another way. So we've got a balanced reaction here, an equilibrium system. We are given the equilibrium constant. Here it's 15.4, so that's our KEQ. Again, we're given a temperature, which we're going to ignore. We don't need to use it to do our calculations. And we've got a concentration of nitrogen and a concentration of hydrogen at equilibrium. Alright, So again, if we take a look at our KEQ expression, we'll have a concentration of nitrogen times the concentration of hydrogen, which will be cubed, and in the denominator the concentration of ammonia squared. If we look at what we know, we're given KEQ, it's 15.4. We're given the concentration of nitrogen, 0.035 moles per liter. I'm going to omit the units since we've learned that the units aren't going to be very meaningful because KEQ doesn't have units that they'll be able to cancel with. Hydrogen, 0.54 cubed, and in the denominator the concentration of ammonia squared. So we want to solve for the concentration of ammonia. We can rearrange this, multiply both sides by the concentration of ammonia squared, and divide both sides by 15.4. And so it would rearrange to give us something that looks like this. And since this is a squared concentration, and we don't want a squared concentration, we just want the concentration, if we find the square root of both sides, then we'll get an answer for the concentration of ammonia. Okay, so that's looking pretty good. I just need to find my calculator. So 0.035 times divided by 15.4 equals, and I find the square root, and the number that I get is 0.0. We'll have two significant digits again, so 0.019 moles per liter. So at equilibrium for this system, the concentration of ammonia, 0.019 moles per liter. In your textbook on page 444, you can try questions 31 and 32, see how they go, and we'll try some more together in class tomorrow.